Well, hello. Today we're going to start talking about Chapter 3, Economic Equivalence. The idea behind economic equivalence is if we have something worth $1 today that will buy an item, what do we have to have in 5 years to buy the same item? That's one concept. The other concept is if I have $1 today and I'm going to earn at a certain amount, 10% a year, in 5 years, how much money do I have to have the same purchasing with those earnings? And so economic equivalence is an attempt to form at a constant point in time what is the value of something under conditions of interest paid or earning power so we can make rational comparisons. Now, by the way, I have a new tablet here today. My old tablet broke, and so I'm getting used to it. I hope it'll work well, but if I have a few problems, I'm sorry. I'm just getting used to the new tablet. Now, the another way to say economic equivalence is we're interested in what is the time value of money. That is, if I have a dollar for a month, how much of the value of that dollar did I use up or gain? It depends, of course. I gained it if I invested it and earned money. I lost it, of course, if inflation was going on, so prices kept going up and I kept the same dollar. And so it is a concept that I think is intuitively clear but has many aspects in the definition. Now, there are a number of unique terms. I'll try to make sure I use the terms in your text and the symbols in your text. If I forget and I use something different, let me know. I'll try. Economic terms are just like terms in electrical engineering. You can have an emitter follower, you can have a unity gain high frequency buffer, you can have all sorts of different things, and different terms relate to the same item depending on who's using it, what company, what the time frame, what the reference is. So I'm going to try, of course, since terminology is, I understand, for everyone, one of the more difficult things to grasp and keep track of, I'm going to try very hard to keep the same terminology as your text. You should be aware you might go look up these formulas in a different book or on a spreadsheet or something, and you say, hey, they've got all different symbols. Well, okay, they do. These things are not universal, and you just have to learn to understand by context what's going on. We do that intuitively in our own field of electronics, so you need to be able to do that in the economic world as well. Well, if we start looking at some of the terms, oops, see, I have to get a little used to it. Some of the terms, to read some of the terms, I would refer you to page 62 in your text, where they give their definition of these terms. Some of the key terms, first they talk about capital A sub little n. Now, capital A is referring to a payment. Little n is referring to what unit of time. So let's say I have to make a payment every month for 5 months of $100. A sub 5 would be the $100 I paid in month 5. Now there is on payments or income, there is what's called an end of month. End of month. There's an end of month convention. And the assumption on end of month is that anything I pay or anything I get happens at the end of the month unless I'm told elsewise. Or if we're not talking end of month, maybe we're talking end of year or end of week. So it's really more generally the end of the interval. Now, interval is something we specify when we're talking about economic terms. Is the interval of interest a month, 2 months, 6 months, a year? If you're taking out a financial transaction for something annual, let's say you're making an annual payment, if you make the payment in the middle of June, or you make the payment in November or December, they're all assumed to happen the last day of the year. This is done for convenience, so you have to keep track of the days and so forth. It is a long convention. If you go to the tax code, if I take out a loan in January, it's the same as tax code wise, taking it out in December. And so this explains why lots of things are done in December, lots of financial transactions, because I can, for example, buy a machine in December and start using it in December and only pay for it in December, yet for purposes of tax, of figuring out my expense and tax, I bought it in January. So there's lots of different transactions that are driven by this convention. Well, then there's capital N. That's the number of intervals. So it's the number of intervals. Now I realize right at the moment my writing is not being very good on this because, as I said, a new tablet. I will get better. But really, it's not so important what I wrote. You write things to emphasize the point, but that's what you can see the definitions on page 62. There is something that we call P. This is the present value. Present value is just that. If I had $1, it's present value right now. Present value is $1. Now, I could ask you the question, if I have 10% inflation and in 1 year I have $1.10, what is the present value? Well, it's going to be 10% less, so it's going to be $1. So that's what I mean by present value. What is the value of something in terms of buying things that I have right now? Then there is capital F. That's a future value. Future value. The idea is simply that if I have $1 now, and in a year's time I'm going to have to buy the same thing, how much does that dollar buy? So if I had $1 now and 10% inflation, at the end of the year it would buy $1 divided by 1.1, where it's 1 plus the inflation. And so at the end of the year it's 90 cents or thereabouts is what the future value is. There is also A, which I set up here without the N, and that's just in general payment, sort of payment term. And so these are some of the main terms. Look at page 62 of the text, and you'll take a look. You'll see what's there. Well, let's go and get a new, oops, let's get a clean sheet here. Okay. Well, in all of this, we are going to try to keep track of what's going on. And so to keep track of what's going on, we are going to use cash flow diagrams. Flow diagrams. A cash flow diagram is simply meant to account for money coming in, money going out. You have a straight line, which is the time axis, and then you have another axis, which is the value, which generally we're talking dollars. So as we go along in time, we record whether we're receiving money or spending money. So for example, let's say I got a loan of $1,000. I put an arrow, generally it's done with arrows. I make the height equal 1,000. I got it today, so the time is 0. It's relative. You could use actual dates. It's more conventional to just use 0. And let's say I had to pay 10% interest on this and pay everything back at the end of the year. So sometime over here, I would have to pay the 1,000 back, and I would have to pay the interest, which would be 100. And so I now have, and this would be at the end of the year, so this would be 1 year. Tablets, 1 year. The net then cash flow would be summing these as they go along. We can sum them in what are called actual dollars, which is what what I've recorded here. That is, it's actually looking at a dollar. And so this would, if I summed all this together in actual dollars, I would say, well, I had spent 100 more than I got. The sum of all this activity is minus 100. Now, of course, the real idea in economic equivalence is to take account of the fact that these dollars out here buy less than the dollar I got. So if, for example, inflation was 10%, then I would have to come out here and I would have to divide this by 1.1, which means this amount is equivalent to minus 1,000. This is plus 1,000. It sums to 0. So this is a cash flow diagram. You always want to use cash flow diagrams because there's often many things happening. I'm getting money, I'm spending money, I'm investing money, and there's many things happening. And we don't want to forget any of the pieces. We're going to add them all together, but we don't want to forget any. And so to make sure we don't forget any, we put them all on the diagram. If we have two happening at the same time, we just stack them up. If maybe we had to pay 1,000, but we got 500, we do it this way. We'd have a minus 1,000 we had to pay, and we'd have a plus 500 we got. So we would have the minus, the plus, and we would be able to see, oh, the net right here is 0, but we understand what the flow is, what the flow in and out is, and it allows us then to calculate what the overall total is. This is important because, like I said, it's easy, very easy to get confused on this. Now, so we have the convention on end of the month, or end of the period actually, whether the period's a year, a month, or a quarter. We have the cash flow diagram. Now we have to look at what do we have for interest. Well, for interest we have two different types of interest. We have, so let's just get a new one of these. And we'll get another pen here. We have two types of interest. We have simple. It doesn't mean it's dumb. It's simple interest. Simple interest is interest that you pay only on the principal. You do not pay interest on interest. So if I have simple interest and I borrow $100 at $10 simple, then that my term, the length of time until I pay it back is 1 year. Then what I will pay back at the end of the year is $110 because it's just 10% more. More generally, what I will do is I will have a number of payments I'm making as well as the amount I eventually turn back. So this means that my total amount of payments, is going to be n times I have to pay. Remember, capital N is the number of intervals. N times I have to pay times the interest rate, because that's how many times I paid. So if I paid 10% January, February, March, April, I paid 10% 4 times, I paid 40%. Remember, I'm not paying interest on the interest. I'm only paying interest on the principal. So the total interest that I have to pay, is going to be the interval interest times the number of intervals times whatever the principal is. And so another way to say it is the total amount that I will have paid in the future at the end of the period. The future value, the sum of all these, is going to be, well, it's 1 plus the interest, which is what I paid per month, per year, whatever, times however many months or year or whatever, times the principal. Now, if I try to do this in a cash flow in terms of the payments, all right, first I would have nothing. The first payment comes at the end, and that's just I times P. The next one is I times P, and I just keep doing that And the last payment then is the principal. I have to pay all the principal back then, plus I times P. And so I add all these up, I get this. This is a very simple formula. It's called simple interest. It is often what people think of and talk about. It may or may not be similar to what's actually charged, and which is compound interest. So we have this formula. We understand what it means. Let's talk a minute about compound interest. What is compound interest? Well, compound interest is generally what we assume that people are paying because it is most common. It's called compound interest. Compound. Compound interest, you pay interest on the interest. So, for example, if I'm getting, let's say I'm going to pay 10% interest per month, and I say it's compounded. If they don't say anything, you assume it's compounded, by the way. So I really shouldn't have to say it, but it's compounded. Usually, though, you have to know how often it's compounded, over what period. And the period or the interval that it's compounded on then is the compounding rate. So let's say I have a interest rate of 10% per month, compounded monthly. What does that mean? Well, it means if I borrow $1 and I borrow it for 6 months, at the end of the first month, what is really due is 1 plus 0.1, 1 plus 10%, times $1, $1.10. But I'm not paying it yet because it's not due for 6 months. So the next month, I charge 10% on what I owe. Well, I owe $1.10. So now I have $1.10 times 1 plus 10% interest. So I'm charging interest on the interest. So now instead of, so it's 1 plus 1, 1 plus 0.1 squared, or $1.21. Third month, we do it again. Fourth month, we do it again, and so forth. At the end of the 6 months, we're going to have, roughly speaking, $1.70 instead of $1.60 because it's compounded. And so compounding, what you get is the first month, right off the bat, you have what you got. Then you go to what you got times 1 plus the interest rate. But then you go to what you got times 1 plus the interest rate times 1 plus the interest rate. And, or in other words, you just square that. And so you can see that ultimately, where you're going to go is you're going to go the principal times 1 plus the interest rate raised to the power of the number of terms in the period. Interesting. So that's what you'll ultimately get to. So we write this more generally as a principal after n compounding periods is equal to, I said the principal. I should have said the future value. The future value is equal to, well, it's equal to what I borrowed times 1 plus the interest rate raised to the power of the number of compounding periods. Now you can see what's going to happen. I mean, it's pretty clear. What's going to happen is simple. It's going to go a straight right line, and compound is going to be curved. So this is what simple is going to look like, and this is what compound is going to look like. As long as the interest rate is low, or the number of steps or compounding periods is low, they're pretty much the same. The higher the interest rate, or the more the number of compounding periods, the bigger the difference. In real world, pretty much everyone compounds. They're simple formulas. It's just, and of course, what happens, which the people like, is if you're a bank, you get more interest when you compound because it's going up faster. If you're an investor, you get a greater return if it's compounding. Again, it goes up faster. And so you tend to prefer that anyway, and that's what we tend to use. Now, let's just take a quick look at an example. Um, let me assume that I have a 12% rate, 12% per year rate. But it's compounded. Let's see, how much often did I decide to compound it? We said I'm going to have a 90-day term and a 1 month. So I have 90-day term, 3 months. Generally, people will say 90 days, and generally the 90 days is 3 months. They don't actually count physically 90 days. It's 3 months. That's generally what's meant. Again, if it's unclear, you have to ask someone, but for our purposes, if I say 30, 60, 90, 120, it's 1 month, 2 months, 3 months, so forth. A 90-day term, and it's compounded monthly. So we're going to compound monthly. So this is the period over which we're going to compound. So let's take a quick look at that. And let's look at $1. Okay, well, if I have simple, first off, it's compounded monthly. So I want the monthly rate. If this is the annual rate, the monthly rate is just going to be that divided by 12. So the monthly rate is going to be 12% divided by 12 months, or 1% a month. So this is my monthly rate, and I'll need that. Now, let's do simple. Let's just look at simple. What is a simple going to give me? Well, it's just my $1 times 1 plus the number of intervals. I said it's 90 days, so 3 months, and 1% a month, so it's plus 3 times 0.0101, and so I get $1.03. If I compound it, well, now I'm going to have the $1 times 1 plus the 0.01 again. But instead of being 3 times this, it's going to be cubed. Now, cubing it is going to be very close to 3. But it's on the order of, and I say on the order of because I probably should have chosen bigger numbers so that it's bigger spread. It's still on the order of 1.03. It's about 1. It's about 1. You could calculate exactly 1.033, and of course we generally aren't keeping track of fraction of cents. But they start to diverge, and the bigger this is, the greater the divergence. The bigger this is, the greater the divergence. When these are relatively modest, under 10, this is relatively modest, a couple percent. They're very little difference. If they get to be a big numbers, this is 10%, this is 20 periods, that gets to be a huge difference. So how much there is really depends to be exactly on how much and how long. So we have simple and we have compound. Often your interest is quoted as if it's simple. This is a simple rate, quote. But you're then told, well, yes, but it's compounded monthly or daily or whatever it is. All that means then is you take this simple rate and you just divide it to whatever the compounding period is, in this case a month. So there's 12 months in a year, so my actual compounding is 1%, and then you go ahead and you compound it for the number of months or periods involved, and that's really how you use it. It's a fairly straightforward concept, but one that people often get confused with. And so if I were to look at what's going on here, for example, what I would say in that previous example is I would say a present value of $1 is equivalent to a future value of $1.33. We'll just use $1.03 under an interest rate of 12% a year, or often it's called annual. So a 12% annual rate. And then, of course, depending on, in this case, simple and compound were so close, you don't really need to know the difference because you get rounded off the same answer. But in general, then I'd have to tell you, for example, compounded monthly, and the present value is a future value, and I might want to put a 3 there. It doesn't want me to put a 3 there. I'm going to have to work on this some more. 3 there. It's compounded monthly for 3 months. And so that's the basic idea then between of economic equivalence is under what given interest rate that you're paid or you pay. Remember, if you're paying it, then the amount is going up, which is what we are calculating at the moment. I'm paying it, the amount's going up. If I'm receiving it, the amount's going down. And of course, these equivalent relationships, you can write them either way. You can write them going as present equals future, or as future equals present. Because if the future is 1.03 times the present, then the present is the future divided by 1.03. It's as simple as that. And so that is the basic concept. Now, we'll do more with this. But in addition, these are generally written in a straightforward fashion. They are generally written in the format, a functional format. The future is equal to the present times the future divided by the present. So it's the ratio you're really calculating with the interest rate per time period and the number of periods. Now, as we look further and further, there may be more terms here, but this is the starting point. And of course, that means the present is equal to the future times the future times the present divided by the future. Again, you need to know the interest rate and the number of time periods. It's a pretty standard format. You find it in your all sorts of business calculators. If you want to, by the way, as I said, you can use any calculator, buy a financial calculator for $20, $30, and learn how to use it, of course. But these are pretty straightforward sort of calculations, and they're pretty commonly defined this way, so you can look them up. If you go to a spreadsheet and you want to insert a function, you will probably find a function written very much like that. Excel has changed their format slightly in recent years, but I think you'll recognize it. The basic idea, now from this, of course, we are going to do general equivalence. General equivalence means given any cash flow, what is its future or past value? What is it, present or past value? And so the idea that we're really headed towards is, well, here's my cash flow diagram. It's going along. And let's say I have a little bit of money I got there, and then I paid some here, and then I paid a lot here, then I paid almost nothing here, and then I got a bunch here, and here is my end point. And I want to know, well, what's that future value? You see, the reason I might want to do it is maybe I have 3 different machines I can buy. The one machine costs this and has these maintenance costs, but can be sold later on for this amount. And so I want to know what the total cost was. Now I may have another machine that costs more and takes less maintenance. So I want to know what the cost here is, and then I can compare the two machines. So that's the idea of economics, of economic equivalence. Is I get these different possibilities, and I see, well, what did it really cost me? Generally, what we'll be doing is we'll take that and we'll project it to there. Here's a present value, there's a future value, and so I can say, well, this present value is equal to so much in the future. Then I'll take and I'll project this to there, and I'll add it up. Because this one is going to project differently than that one. There's a different amount of time involved. And I'm going to project this one, and I'm going to project this one, and I'm going to project this one. And so I'm going to add all of these 5 things up out here to see what the total is. That will be my future value. These things are completely separable. They are linear equations. And so as we know, they don't interact. You can treat each one on its own merit. And that is where we're headed. Now, one thing I would point out to you is that this is a general case, and we project each one individually and add them up. This is easily done on a spreadsheet. You could do it by hand, as long as you have a reasonable number of terms, 5, 6, or something like that. There are basic formulas we'll look at next. Basic formulas for what if they're special cases. What if you have the same payment every period? That's an annuity. Same payment every period for a period of time is an annuity. What happens if you have a payment that's going up in time? What happens if you have a payment that's going up in a linear fashion? $1, then $1.10, $1.20, linear, and so forth. And these are all special cases of the more general cash flow. This would be a general cash flow. And you project them ahead, and you can answer the question then of what's the future value. Of course, once I know the value here, add all that up, I also know the value there, right? Because all I have to do is I take my value over here and I project it back to there. And so I can also say, well, what's the equivalent in the present or the future? And I can also pick a time in the middle. Once I know a value here, what this cash flow value is there, I can say, well, yeah, but what about right here? Well, I use my same formulas, and I say, well, 1,000 here is worth 800 there. So I can talk about how much this is worth to me at any period of time, as long as I understand, well, what is the interest I'm paying or earning? Depends on whether it's an investment or a loan or something. What am I paying? What am I earning? What is the interval of time? And how many intervals am I talking about? As long as I know that information, I can talk present, future, what's the equivalence. And the goal always is to have a common point in time to compare things. So if I have 3 options on machines, I want to compare all 3 at the same period of time, the same month. And then once I put them in the same period of time, I can make a choice. This is more expensive, that's cheaper. This is 20% more expensive, 30% more expensive. You will not always, in a real environment, choose the cheapest option. There may be other things. Maybe one machine does a better job. Maybe one machine, even though you think it's going to cost something, there's risk. You think it might break down early or something, and you just don't know. There may be quality issues. Maybe one gives a very good product and one's kind of marginal. So we don't always select the cheapest thing, but it is important to understand which is the cheapest and how much more it costs us to make a different choice. Does it cost us twice as much? Well, then we start to ask questions of, what are we getting for that? Is it the quality really worth it? Can our product be a higher price? And so that's really where the whole idea is heading and what you're looking at. Well, that's really as far as I'm going to go in this. I can see I'm about a half an hour gone, so I'm going to call it quits now, and we'll look at it some more.